All right, this video will go through the basics of U-substitution that you need to know for Unit 5. So we have seen that taking an antiderivative or an indefinite integral is not as easy as taking a derivative. And so far we've just learned some basic rules for doing indefinite integrals, but we're going to see as we go further in calculus that we're going to need a lot of different techniques to take integrals. And the one technique that you will learn in this course is what's called U-substitution. Later on, you'll learn integration by parts and other types of techniques. But this is going to let us take certain integrals that we're going to see in this course. So when we are going to use U-substitution, most often is when we get something that looks like a chain rule. So we remember the chain rule back from Unit 3. Okay, and here's an example. The derivative of sine of x squared is cosine of x squared, leave the inside alone, and then multiply by the derivative of the inside. Okay, so we get cosine x squared times 2x. We can go backwards. If I take the integral of f of u du, and when we say this du, we can think of that as being like u prime, which makes it look like this, okay, which means we go back to where we started when we take the antiderivative, and f prime, right, would go back to f. So now using our antiderivative notation, little f would turn into big F. Okay, so to do an example, if we had, say, the integral of cosine of x squared times 2x, well, that came from, right, so right, this is the du, this is the derivative of this. Well, hey, that came from sine of x squared plus c. Okay, when we take the integral, we need to put the plus c, but we can see like, oh, the antiderivative of cosine is sine, and the 2x was the derivative of x squared, so when we go backwards, that 2x is going to go away in a sense, but we're taking this process and now just going backwards. Okay, so let me show you an example, how we're going to use this. Okay, what we want to do is take an integral and get it into this form so that we can more easily take the integral. Okay, so we are going to pick a u. Now, which thing do you pick? That comes with practice, but I'm going to pick this. We'll talk in a minute. How would you know what to pick? Now, what I'm going to do is I'm going to take the derivative of u. So remember, we take the derivative of this. Now, u, that would become du dx. Right, and that would become this. But I need to replace this stuff and make it into just du. All right, so now that I've called u x to the fourth, this is going to turn into cosine of just u. So that's my f of u. But I got to get rid of this stuff and turn it into just du. Okay, so this is 4x cubed. This is 8x cubed. So we just need to manipulate this a little bit. First of all, I'm going to get the dx over. So I'm just going to multiply both sides by dx. And then what I'm going to do is I'm going to multiply both sides by 2. All right, 2 times 4 is 8. Oh, okay, now it matches. So what I can do now is I can say that this integral is the same as the integral of cosine of u times 2 du. And we talked about in class when you have a constant multiplied by an integral, right? C times f of x is the same thing as just pulling the c out, as long as c is just a number. So we can pull that 2 to the front and make this even easier. All right, so now we are able to take this integral. What is the integral of cosine? Well, it's just sine. So this will be sine of u plus c, don't forget that. And now, right, we know u is x to the fourth, so we replace that and we're done. That is the answer. How could we check? Well, we could take a derivative and see if we get back where we started. So let's let y equal 2 times sine x to the fourth plus c. Take a derivative. The constant will just go away. 2 sine would become 2 cosine. And then chain rule. We would multiply by 4x to the third. But if we clean that up, right, the 2 could just come over here. And sure enough, okay, we would end up back where we started. Okay, so this is the general technique. How do we know what to pick for u? Okay, well, that comes with practice. But generally, okay, you want to look for something that is inside of something else. Because again, we're sort of like we're undoing the chain rule. So we want to look for that inner function. And we'll see a bunch of examples. Okay, so last time, we chose the thing inside the cosine. Okay, and we'll see others. Another thing is you want to look for something and its derivative. So last time, we know the derivative of x to the fourth is going to be something with an x to the third. So that's another little trick we look for. All right, or maybe you see a sine, and so then you know the derivative is cosine or something like that, or tan and secant squared, something like that. You get to decide what you want u to be. You don't get to pick du. Du is literally you can think of the d as telling you to take the derivative of u, literally. And this is something that, like, you're going to make mistakes sometimes. You're going to pick the wrong thing for u sometimes, and you'll get stuck, and then you have to just be willing to go back and try again. Start over. All right, so I'm going to go through a bunch of examples. At any point, feel free to pause and try it yourself. All right, and this will be a longer video, so halfway through, I'm going to suggest you go do some practice on your own, and then come back to this video for the remaining topics. All right, so here's an example. So I'm going to pick my u to be this, okay, x squared plus 7. Again, I'm looking for something inside of something else, so this is inside the square root. I'm also thinking, hey, if I take a derivative of x squared, I know that's going to be 2x, and that's going to be matching up with that. Okay, I'm going to find my du. Now, last time we did du dx, but from now on, because you're just going to move it over to the right, you can just start by putting it over there. That's okay. And the derivative of this is going to be 2x. So you don't have to do the du dx and then move the dx over every single time. You can just start by doing that. But now I wanted 10x. But I only have 2x, so now I'm just going to multiply both sides by 5. All right, so now we're going to rewrite the integral as the square root of u times 5 du. And so this becomes u, and then this is all multiplied together, so I could just move the 10 over here if I wanted, put the 10x and the dx together, and replace that with 5 du. Okay, like last time, we pull the 5 to the front. And now, right, using power rule, think of that as u to the 1/2, I can take that antiderivative, so this becomes u to the 3/2 over 3/2. Right, and then I'm just going to clean that up. So take the reciprocal of that, that would be 5 times 2 is 10 thirds. And then take what you did for u and plug that back in. And that's your answer. And if you took the derivative of that, you would end up back where you started if you wanted to check. Okay, another example. So looking at this, I'm going to let this be my u. Okay, which means my du is going to be 6x to the 5th dx. But I only want 2x to the 5th. So I am going to multiply both sides by 1/3 to get it to match. Now I'm going to set this up. Okay, this is going to be e to the u. And now, we could put in the 1/3 du, but you've seen now in 2 examples, right, that 2 just came to the front, and that 5 just comes to the front. So you can take a little shortcut and just put the 1/3 in front. You don't have to do that in 2 steps. Right? Now take the antiderivative. The antiderivative of e to the u is e to the u. Right? That's an easy one. And then put back in your, what was u? It was x to the 6th plus 11. And you're done. Another example. Okay, cosine of x to the 3rd, so I'm going to let that be my u. Again, it's inside of something, so it's a good choice. Find my du. I want 12, so I multiply both sides by 4. And that matches that. So now I can substitute. Again, just take whatever number you have here and throw that in front. This is going to become cosine of u du, which is simply going to be sine plus c. And then fill in my x. And that's my answer. Once you get the hang of this, it's not too bad for the more basic examples. So maybe you want to try this one yourself, right? Pause the video if you want. All right, and now I'll go through it. Take a derivative. But I want 2x, so I'm going to do 1/8. And now replace. Put the 1/8 in front. The cube root of u, which I can think of as being u to the 1/3. So that's going to be u to the 4/3 over 4/3. And then I'm just going to take the reciprocal, bring that up, right? So that's going to be 3 over 32. And then I'll just put my x back in. So 8x squared minus 10 to the 4/3 plus c. And that's my answer. All right, one other thing is just when you have a fraction, sometimes you're going to get a little confused about what to do sometimes. So this will not always work, but it's a good idea to try letting the bottom be the u. If you're not sure what else to do, because when you take a derivative, and we'll get this, okay, well that's almost that, so let's make it 10 by multiplying by 2. Okay, when you set this up, put the 2 in front, the bottom becomes u, and remember this is really multiplied, so that all just goes together, and so the du will go on the top. So you would look at that and maybe you'd be confused. So remember, you can think of that as really being 1 over u times du, but we know that rule. Okay, we learned that 1 over x goes back to being ln of x, right? Just like when the derivative of ln is 1 over x. So this is going to be 2 times the natural log of the absolute value of u plus c. And then we plug that back in. And you win. Okay, another example with that would be tangent. So, okay, how do I do this? Well, you would need to be just a little bit clever and realize that, okay, tangent is really sine over cosine. So now, initially a lot of students will pick u to be sine because they know the derivative is cosine, but then you'll get stuck. So it's actually easier to pick the bottom, cosine of x. The derivative is negative sine. That's going to allow us, we don't even have to manipulate this, we just move the negative sign over, but right, this is going to go straight to being du over u when we do that. And so the answer is going to be negative ln, which is going to be negative ln of cosine plus c. All right, one final example for you to try. Again, pause the video if you want. All right, so I let my u be this, and my du, therefore, will be this, okay, which is almost that. If we divide it by 12, that'll work out. Okay, so you're just trying to make it match exactly. And now we can set this up. Put the 1/12 in front, du over u, which is 1/12 ln of u plus c, and then fill in your x. So 4x cubed plus 12x plus c. So those are the more basic examples. At this point, you may want to go on Canvas, find 5.5 day 1, and try the 4 practice problems that are there to make sure you're understanding the concept before you move on to the more complicated ones that I'm about to do. Okay, so this is sort of the second half of this video. This is what we did on Friday. The definite integral, remember, represents the area under the curve from some point to some other point. We have been doing indefinite integrals to this point. Now we are going to look at a definite integral, and we just need to learn this idea that is called a change of bounds. So, looking at this integral, we're going to do a U-substitution. And we want to make it match, so we'll get this. Okay, so all of that is the same that we were doing before. I'm going to go to set this up. So this is going to turn into 1/3 in front, u to the 4th du. But these bounds need to change because I'm using a different function. Originally, I was trying to find the area under this function, which, I'm not quite sure what it looks like, but, it could have been, some wavy thing and could have been something else. But this is just going to be straight up u to the 4th. It's a completely different function. And so there's no guarantee that the area from 0 to 1 of this thing is going to be the same as the area from 0 to 1 of this thing. We need to check by doing something called change of bounds. And all that is we take these numbers and plug them in for u. So we do 1 cubed plus 1, which equals 2, and we do 0 cubed plus 1 equals 1. So we take our x values and plug them into what u is going to be, and those become the new u bounds of my integral instead of my x bounds. Okay, so we're changing the functions. We also need to change the bounds that we are integrating. Now we do what we always do. Leave the 1/3 in front, take the antiderivative. We don't need a plus c because we're now going to plug in 1 and 2. All right, we're taking a definite integral, so we want to do big F of b minus big F of a, right? The fundamental theorem. So this will become, I'll just clean this up and multiply the 1/3 by the 5. So this will be u to the 5th over 15. And now I will plug in 2. Okay, so we just go right to plugging it in, and then I will plug in 1. And that's going to be 32 minus 1, so 31 over 15. So this time we get a number, and that number again represents the area under that function, or the accumulation of area anyway, of that function from 0 to 1. Okay, we'll do one more example. The integral from 5 to 3. Okay, so again, I'll pick my u, get my du, manipulate it to match. I will also now plug in my bounds into the u expression. So I'll say 5 squared minus 9, and 3 squared minus 9. Well, 3 squared minus 9 is 0, and 25 minus 9 is 16. Those become the new bounds of my integral. And this will be this with a 4 in front. And now I'll take the antiderivative. Okay, the antiderivative is going to be 2/3 u to the 3/2. And then we'll go straight to plugging in our bounds. But this is nice. We can just leave the 4 in front, by the way, because the 0 is just going to go away. Right? That's just going to become 0. So we just need to know, okay, 16 to the 3/2 power is going to become 64. All right, and we would, you would have a calculator on the test, so you could clean this up, but I will tell you it comes out to 512 divided by 3. Okay, so these are a little bit different in terms of how you finish the problem, but the way you set it up is the same. The only difference is you need to also figure out your bounds of your integral. All right, so that's one thing we learned. The other thing that we learned is what we can do when the inside function and the outside function have the same degree. So we have seen integrals like this sort of thing so far, where we start with like an x to the third, but then we know when we take the derivative of that, we're going to get the thing on the outside, maybe just, with a constant in front we got to take care of. All right, so what do we do if it looks more like this now, where we have x and we also have x? Okay, well, we're still going to use U-substitution. And we're still going to follow our intuition, like let's pick the thing inside of something else. Let's still take a derivative, but the derivative of x is just 1, so we can just say dx. Now, we can substitute for this part. All right, we can say u to the 20th power. We can substitute for this part. We can just say it's du, but we still have this pesky x on the outside. Okay, so the key here is we can realize that's an equation, so I can rewrite it. Right, if u equals x minus 2, that means u plus 2 equals x by just rearranging that. And so I can make a substitution now for just x, like so. Now I'm going to try to take that integral. Okay, so first of all, I'm just going to think of this without the parentheses. I don't want to take this just yet. It would be a lot easier if I distribute that in. That's going to be u to the 21st power plus 2u to the 20th power. All right, so just using the distributor property. Now I'll take the integral. That's not too bad. Use power rule. 2u to the 21 over 21. Now you need a plus c, right? This is an indefinite integral, so still need that. And then, of course, you put your x back in at the end. And you win. Never said it was going to be easy. Okay, I will go through a few more examples like this. All right, same idea. I'm going to pick the thing inside of something else. That won't always work, but usually it's a good idea. All right, the derivative is, well, again, like before, just dx. I'm also going to rewrite x in terms of u. Okay, so I'm just going to rearrange that formula. And now I'm going to set this up. Where there was an x, I'm going to replace it with u minus 2. Obviously, we're going to clean that up in a second. This will just become u, and this will become du. Right? So think of it as like there's 3 things that you need to replace. And where there was an x, we're instead writing u minus 2. Now, of course, immediately you can make that into u minus 5. And then, like last time, we distributed the u to the 20. So we're going to distribute this by thinking of it as u to the 1/2. And this is really u to the 1. And so we would add the exponents. That will become u to the 3/2 minus u to the 1/2 times 5. And now we take the antiderivative. So this will become this. And this will become, let's see, 10 over 3 u to the 3/2. And then fill in your x as always. And that's your answer. And although you could check this by taking a derivative to see if you got back where you started, I wouldn't do that. That's going to be a lot of work, but you could. All right, one final example here would be something like this. Now this looks kind of the same, and it is. We're just going to see it's a tiny bit more complicated. Okay, so I'll start by picking this because it's inside of the 15th power. Take my derivative. Now, careful, I get 2x, right? So this is 2 dx, which means I want to get that alone because I just want dx. And then again, I'm going to rewrite x in terms of u. So add 5 to both sides and divide by 2. Okay, we're going to set that up now. I'm going to pull the 1/2 in front. I'm going to put in where there was an x. I'm going to replace it with this. And then this just becomes u to the 15th, and that becomes du. All right, now we're going to clean up. So first of all, I'm going to combine these by remembering that 1 is really just 2 over 2. So combining the fractions and combining like terms, this becomes u plus 7. And then, we think of this as really being 1/2 times this. So I can pull the 1/2 out of the integral, and it will just multiply by what's already there. So it'll become 1/4 u plus 7. All right, and now we know we can just distribute. Okay, so this is the same type of problem, but this 2 back here just causes a little bit of extra algebra that we have to do to get to the final result. That's all. All right, so we'll finish the problem. 1/4 u to the 16th power. All right, and then finally, you can just leave the 1/4 in front. This will be u to the 17 over 17 plus 7, u to the 16 over 16. And then we'll fill our x back in, and we're done. You can just leave the 1/4 in front, that's fine. And you win, that is your answer. All right, that covers everything that you need to know about U-substitution. So if you go on Canvas, you will see U-sub practice 2. It's a file, not an assignment. So just go to the Unit 5 module and you'll find it. The answer key is there. It practices these techniques that I just went over, along with the more basic types as well. If you have any questions, feel free to send me an email or talk to me on Monday when we go over this. And otherwise, thanks for watching. I hope this helped. I'll see you in class.